In this tutorial we will look at each of the different types of rock and how they interact in the rock cycle, and then look at examples of each type in more detail, hopefully to enable the student to be able to identify rocks in an exercise. Rocks are aggregates of crystals, or non-crystalline masses, of different minerals or of grains, depending on how they have formed. There are three main types of rocks as defined by how they are created. Igneous rocks crystallize from a molten rock material called magma. Metamorphic rocks are created by the recrystallization in solid state of pre-existing rocks, which could be igneous, metamorphic, or sedimentary types. Sedimentary rocks are created by the deposition on the surface of the earth of grains derived from pre-existing rocks by weathering, or by the deposition of grains derived from shells or skeletons of organisms, or by the crystallization from solution of various minerals. Sedimentary rocks can therefore also be subdivided into three categories based on how they are deposited: clastic, organic, and chemical. The different rock types interact in a cycle of creation and destruction known as the rock cycle. Sediments on the Earth's surface generated by weathering, combined with organic detritus and crystallized minerals, combine to create sedimentary rocks as they are buried by the deposition of more sediment layers above. If they are buried far enough, the pressure and temperature increase forces a number of reactions to take place, replacing unstable minerals with new minerals and growing the size of those crystals as metamorphism continues. Bury a rock far enough and it will reach the melting point for rocks, which will result in the development of liquid magma. If the magma is then permitted to cool, perhaps by rising some distance through the crust, then crystals will start to form, creating an igneous rock. Looking at rock samples can be difficult, but there are lots of things that you can observe that help you to place each rock sample in the three different categories, and then within those categories into subcategories based on composition and mode of formation. You are looking for the difference between crystalline structure and rocks containing grains. You are looking for evidence of layering or other textural differences in crystals or grains, and you are looking for evidence of fossils, that's the remains of organisms deposited with the sediment. A key thing to be aware of when looking at rock samples and at outcrops is the issue of weathering. Weathering is the effect of exposure to the atmosphere and water on rocks, which results in the decomposition of unstable minerals and the breaking of the rock up into smaller grains. Weathering creates on an exposed rock surface a crust of weathered material that is quite dissimilar to the fresh surface of the rock, as can be observed in a broken surface. For this reason, geologists commonly carry hammers to break rocks off outcrops so they can observe fresh surfaces. When looking at a rock, in hand specimen or an outcrop, ask yourself if what you are seeing is part of the weathering activity, or even growth of moss or lichen on the surface of the outcrop, or is it part of the real rock that you are trying to observe? Watch out for colour changes. Weathered surfaces often have reddish-brown coloration due to oxidation of iron, or texture changes, softer slimy feels, and distinct plant or algae materials being present. Pebbles that have smooth surfaces from erosion in rivers and the sea have weathered surfaces but more often display clean unweathered surfaces and are a good place to look for distinctive rock textures and structures. Now we will look in more detail at each of the three types of rock. Igneous rocks. Igneous rocks crystallize from magma, so let us start with what is magma. Magma is molten rock. The melting temperature of a rock depends on its composition, but all rocks will be molten by 1200 degrees centigrade. Some minerals will start to melt at much lower temperatures, as low as 600 degrees, and the presence of water in the rock will significantly lower the melting temperature of all rocks. 1200 degrees is reached at the base of the lithosphere, that is the solid rock-like part of the surface of the Earth on which we have the crust that forms the outermost rock layer of the Earth. Lithosphere is solidified mantle material, and it is solid because it is cooler than that critical melting temperature. The mantle is, loosely speaking, liquid and moves within the Earth in convection cells. Hot magma rising from closer to the centre of the Earth can rise up through the lithosphere and either intrude within the crust or erupt at the surface, Either way, it cools sufficiently that crystals form until the rock mass is solid. Magma can also be formed when water is added at subduction zones, lowering the melting point of the rocks around the subducting plate. Volcanoes are therefore associated both with points of plumes of rising magma and with subducting plate boundaries. Intrusive igneous rocks occur when the magma becomes stuck at depth and cools slowly, allowing all the crystals lots of time to grow, so that the final rock has a coarse crystal size. Extrusive rocks occur where the magma erupts at the surface, cooling rapidly and therefore ending up with very small crystal sizes, or in some cases, that of volcanic glass, obsidian, with no crystals at all. In order for an extrusion or volcano to form, the magma must rise through the crust, forming a number of cross-cutting igneous bodies in the process. Small volumes of magma intruded in the subsurface often cool relatively quickly, if not quite as fast as extruded magma, forming fine crystal-sized versions, even though they are technically intrusions. Dikes are vertical intrusions, and sills are those that form, often to the side of dikes, horizontally, or at least bedding or layering parallel. The composition of the magma determines the composition of the rock which forms. Some magmas, those derived from the mantle, are rich in iron minerals and poor in silica, a composition known as mafic. These form dark-coloured igneous rocks, gabbro, or even pyroxenite in their intrusive forms, or basalt in the extrusive form. However, during the process of rising through the crust, magmas can fractionate. Some minerals crystallise out and are left behind when the rest of the melt moves away, or they can absorb some of the surrounding country rock to change their composition. They become progressively more silica-rich or felsic. These rocks tend to be pale-coloured. If quartz-bearing, they are called granite, which is the intrusive variety, or rhyolite, which is the extrusive variety, or if they're solely composed of feldspar, they are called syenite, intrusive, or trachyte, extrusive. An intermediate composition between these extremes is called diorite, intrusive, or andesite, extrusive, and is very common in continental volcanoes above subduction zones. Metamorphic rocks. Metamorphic rocks are those that are created by recrystallization of rocks while in solid state. This occurs when the pressure and temperature conditions of the rocks changes significantly, either by heating from, for an example, an adjacent intrusion, which is called thermal metamorphism, or by a combination of increased heat and pressure which occurs during deep burial or mountain building events. This is called regional metamorphism. The recrystallization occurs when minerals which are no longer stable in these new conditions are replaced by minerals which are, or where minerals simply recrystallize into new and larger crystals as permitted by the stress regimes present. Where the driving mechanism is only heat, the recrystallization generally does not have an internal texture or layering, or may mimic any original layering derived from the parent rock. However, under regional metamorphism, the application of pressure in various directions means that the recrystallization tends to develop in layers perpendicular to the maximum compressive stress. Especially platy minerals like micas tend to grow only in this orientation, creating schistosity, a layered fabric with splitting along the micaceous layers. Higher grades of metamorphism means larger crystal sizes. Basically, the higher the temperature and the longer the time in residence at these higher temperatures and pressure conditions, then the larger the crystals can grow. Eventually, the temperature may increase to the point of melting some or all of the minerals. Very high-grade metamorphic rocks are commonly cross-cut or interspersed with bodies or veins of igneous rocks. In regional metamorphism, the lowest grades are called slates or phyllites, where higher grades are schists and gneiss. In thermal metamorphism, the first stage is individual mineral growth called a spotted rock, and then complete recrystallization into hornfels. In most cases, thermal and regional metamorphism involve no change to the bulk chemistry of the rocks, so that a mudstone or muddy sandstone follows the route of rock types outlined previously, but rocks with unusual bulk composition end up in different places. The most common unusual compositions are pure quartz sandstones and limestones. These become quartzite and marble respectively, regardless of the mode of metamorphism. However, there is one type of metamorphism where there is a change in chemistry. This is called metasomatism and involves the circulation of hot fluids. Hot fluids dissolve some minerals in the rock mass through which they pass, and then can cause both dissolution and precipitation of new minerals in rocks through which they subsequently pass. The derivation of the hot fluids could be from magmatic bodies. Metasomatism around granitic intrusions is a common place where important ore minerals are created. However, hot fluids are also often associated with fault zones, and metasomatism can occur with and around the fault zones. Sedimentary rocks. Sedimentary rocks are those deposited at the surface by a number of different depositional processes. We will consider our sedimentary rocks in their three separate subdivisions based on how they are formed: clastic, organic, and chemical. Both clastic and organic sedimentary rocks are composed of grains, while chemical sedimentary rocks are crystalline, but may contain fossils or other indications of their sedimentary origin. These categories are not entirely exclusive. Clastic rocks may contain fossils from organic shells or processes, while all sedimentary rocks contain some precipitated minerals known as cement. Clastic sedimentary rocks are created by the erosion of pre-existing rocks, the transport of the sediments that are created by that erosion process, and the deposition of those sediments in some place where there is space available in which to deposit sediments. This is called accommodation space. Clastic sedimentary rocks are classified primarily on the basis of their texture or grain size. The largest grains are likely to be close to the source of the weathering of pre-existing rocks, while fine grains are likely to be found further away as the transport processes further cause breakdown of the grains. Further classification is based on the composition of the grains, mainly on the relative proportions of the main framework grains, quartz, feldspar, and rock fragments. Organic sedimentary rocks are formed from materials derived from plants and animals living within or adjacent to the depositional environment. On land, plant material may accumulate, creating layers of peat that are compressed over time to become coal. In lakes and in the sea, animals and some algae developed calcareous or siliceous shells that on the death of the organism can accumulate in layers on the floor of the sea or lake. Layers of carbonate materials become limestone over time, while siliceous organisms either become flint nodules, where the siliceous skeletons form a minority of the accumulating sediment, or layers of hard silica called chalcedony or chert. Chemical sedimentary rocks form where various minerals precipitate out of solution to form layers or mounds of crystalline deposits. Calcite can precipitate out of solution in cold waters, often at springs or falls, or at hot springs, or within caves as water evaporates. Silica can precipitate at hot springs, while calcite, gypsum, and halite precipitate out of evaporating salty waters. In addition, weathering can cause precipitation of iron oxides within underlying rock or downstream of the weathering location. In the situation where we have fossils in a clastic rock or clastic material in a limestone, the rule of thumb is to look for which is the majority type of grain. If carbonate material is more than 50% of the rock mass, then it is a limestone, a muddy limestone perhaps. If sand is more than 50% of the rock mass, then it is a sandstone, a shelly sandstone perhaps. Similarly, we use important accessory minerals like mica or glauconite to differentiate our rock names, a micaceous sandstone or a glauconitic limestone, for example. Hopefully, we can now sum up with some general observations about each type of rock and how we might identify it in an exercise. Igneous rocks are crystalline. Although generally composed of crystals of all the same size, in some cases phenocrysts may form which will be of a larger size to the surrounding crystals. Igneous rocks do not generally have any internal texture or arrangement or layering, but you may sometimes observe the edge of an igneous rock body or vein as it cuts across pre-existing rock units. Fine-grained igneous rocks formed by extrusions may contain vesicles, gas bubbles. Coarser, intrusive igneous rocks will be solidly crystalline. Metamorphic rocks are also crystalline. However, because the recrystallization process occurs under pressure, in regional metamorphism, they are commonly layered, in that different mineral types will tend to be concentrated in alternating layers, and that platy minerals, like mica, will tend to form in alignment with minimum stress. Low-grade metamorphic rocks may still be largely granular, like slate, whereas higher grades will be completely crystalline and may have very coarse crystal sizes, like gneiss. Sedimentary rocks are always layered. However, at the scale of a hand specimen, this is not always obvious. If you see layering combined with clear grains or the presence of fossils, however, then this will always be a sedimentary rock. Clastic sedimentary rocks will either have clear gravel or sand-sized grains, or may be too fine grained to see with the naked eye. It applies to mudstones and claystones. Organic sedimentary rocks are often best identified by the presence of the organic remains in the rock, and chemical sedimentary rocks by the crystalline structure of the minerals present. This tutorial should help you now to move on to looking at some samples of igneous metamorphic and sedimentary rocks and identifying them based on the information in this tutorial.